Okay, so I know that you all look forward to the presentation of this distinguished paper. I am honored to present on behalf of all the authors who are also my colleagues in Zhejiang University. So first of all, let me give a brief introduction of power inverters. So nowadays, facing the global climate change, we have more and more renewable energy sources. However, the most of them cannot be fed directly into the grid. So what are power inverters? They are used to transform the DC power from renewable energy to the AC power on the grid. However, this is a challenging task because if the frequency of the DC power drop by 2 hertz, it will induce a shutdown from the grid and may cause localized power grid blackout. So in this paper, actually, we explore the possibility of a certain kind of attack on the power inverters. The goal of the attacker is to cause the power inverter to shut down, to reduce the power, or even burn physically damage the power inverter. However, we restrain that the attacker cannot touch or physically damage the inverter. And finally, we assume that the attacker has some prior knowledge of this of the target inverter. So first of all, in order to realize this attack, first let's look at how power inverter works. So the power inverter includes 2 stages, the DC to DC and DC to AC. The DC to DC stage transforms the substandard input voltage into standard bus voltage, and the DC-AC stage converts the standard DC voltage into the standard AC voltage. And both stages rely on this vital sensor called the voltage or current sensor. So what if these sensors go wrong? So there are 3 possible consequences. The first is that during the input control, if the feedback from the sensor is incorrect, we will have suboptimal powers. So this is called damping. And at the output side, if the output control receives wrong reading from the sensors, it will cause denial of service. And finally, for the bus voltage control, there are 2 cases. So if the real voltage is lower than the reading, it will trigger the protection mechanism and lead to DOS attack. However, if the real voltage is higher than the sensor, the real voltage will increase, and finally, it may exceed the threshold and cause the physical burnout, which we will show in detail later. Now, first of all, let's explore the feasibility of such an attack. Can we use EMI signal to affect the readings of the sensor? So in order to do so, we conduct a frequency sweeping test, and we show that indeed we can cause the offset on the voltage and the current sensors, and the offset may either be positive or negative. So to explain our experiment results, we actually answer 3 questions. The first question is, why does the injected AC noise, that's the EMI noise, transformed into a DC offset on the sensor? And the second question is, why the offset be both positive or negative? And the third question is how to achieve controllable manipulation. Now, let's first look at the first question. So why does the AC noise induce a DC offset? So let's take this voltage sensor as an example. So when we inject an EMI signal, it will introduce the noise on the PCB boards, and this amplifier will receive this noise and rectify the signal and amplify the signal, and finally through the filtering phase, the signal will transform into a DC offset. So the answer is that the operational amplifier converts the AC noise into the DC offset. The second question, why does the offset be both positive or negative? So the answer is that we have two inputs into this amplifier. They have different length, so the injected noise will have different coupling frequencies on those two inputs. So because this amplifier adopts a differential algorithm, actually the remaining voltage may be either positive or negative. So that's the answer for the second question. The answer to the third question is that as we try that the amplitude modulation can achieve the goal of controllable manipulation of the sensors. So here is the equation with AC as the amplitude, SM as the modulated signal, and FC as the carrier frequency. And we have conducted the sensor manipulation experiment in our within our lab, and we show that we can both decrease or increase the sensor readings and inject either a triangular or sine wave into the sensors. Okay, so after we have achieved controlled manipulation, then we show how we realize these three types of attacks on the power inverter. So first of all is the DOS attack. So we recall a little bit. We can realize the DOS attack on both the DC side and the AC side. For the DC side, actually, we can incur a sudden change of the reading of the sensor, and this sudden change will trigger the protection mechanism in the power inverter and lead to denial of service attack. And we have shown that using the AM manipulation, actually we can achieve this goal. Okay, on the AC side, if the measured current signal is higher than the threshold, a protection mechanism will be triggered, and it will also lead to the DC attack. So we actually inject a sine wave into the readings of the current sensor and trigger the protection mechanism. So that's the DOS attack. The second one is very interesting, the damage attack. So the damage attack is similar to, but different from the DOS attack. So the key here is that we want to manipulate, we want to alter the sensor reading. However, we do not want to trigger the protection mechanism, which means we need to subtly manipulate the sensor. So here, the damage attack is actually goes like this. So we manipulate the sensor readings to be lower than the real voltage values so that the real voltage will increase as a compensate. So it will increase gradually and finally exceed the threshold and trigger the burnout of the power inverter. So these are the signal designs. So first we use the frequency sweep to find the signal that can trigger sensor reading decrease, and then we just play that signal, gradually increase its magnitude. Finally, the damping attack. So the damping attack here is just that if the sensor reading is different from the real one, it may mislead the optimization algorithm in the power control. Actually, this algorithm cannot converge to the optimal point. So what we do is that we inject two types of frequencies, F1 and F2. One increase the reading, one decrease the reading, so it kind of creates the noise that lead to non-convergence of this algorithm. Okay, interesting part, evaluation. So we evaluate firstly, we evaluate sensors. We use 4 analog sensor and 3 digital sensor, and we show that we can successfully induce positive or negative offsets on those sensors. And then we evaluate whether it's possible to realize those attacks. Okay, so first one is the DOS attack. If you are interested, you are welcome to look at the demos here. And the damping attack, we can do that. And the damaging attack, we do not encourage you to do that by yourself. Okay, and finally, we conduct attacks on the power inverter, and we evaluate the distance and powers. And there is even a real-world evaluation. We actually conduct a simulated attack on the 400, that is kilowatts microgrid in real world, and show that this attack is feasible. Okay, so possible countermeasures may be hardware modification or shielding or detection. So we also construct a portable attack device that can be carried and carry out this attack. So in summary, we have introduced this security issue of power inverters, and we propose 3 impacts that cause these attacks, and we successfully implement those attacks. So if you are interested, you are welcome to visit this website. And I think I will be able to take some simple questions. Thank you.
Okay, yeah. If you have any question, yeah, please come to in front of mic.
Hi, thanks. Really excellent work. I was wondering, like in a real-world attack scenario, like in that case study that you mentioned, how would the attacker determine the signal frequency? And I was also curious about what the signal power output at the antenna was, like the radiated power. Thanks.
Okay, I will spend more time explaining our real-world experiment. So you can see in our real-world experiment, we show that we can decrease the frequency of this microgrid, this real microgrid, by 2 Hertz. And after this part, we are not able to continue the experiment due to ethical issues. So these parts are simulated. So we simulate that if we further decrease the frequency, we will be able to induce the power outage. So the final part are simulated.
Okay, let's thanks to speaker again.